This is problem 25 from the 2020 DMC 10. The diagram below is composed of 5 triangles forming a regular pentagon. How many ways are there to color the 10 edges in the diagram with red, blue, or green in such a way that no vertex of a triangle has 3 or more edges connected to it that are the same color? Rotations and reflections are considered distinct colorings. Cool. So the first thing we're going to think about when we look at this problem is that center vertex. The center vertex has 5 edges connected to it, and we don't want 3 or more edges with the same color connected to it. So we're going to deduce, actually, that we're going to have something like this, where we have 2 edges of one color connected to it, 2 edges of another color, and then finally 1 edge of a final color. And so there are actually kind of 3 distinct ways to have these edges arranged. And so we're going to split that up into 3 different cases and then add up the number of arrangements we get from each of our cases to get our final answer. So the first case looks something like this. We're just going to set the colors at random here, just as a disclaimer, and then we're going to multiply later on to account for kind of fixing those colors at random here. But anyhow, when we fix those colors at random, we'll just say we have kind of like 1 red here, 2 blue here, and 2 green over here. And then we have these 5 edges on the border, which we still need to complete. So we're going to use pi, or the principle of inclusion and exclusion, to do this problem. So we want to find how many arrangements actually break our requirements that no vertex has 3 or more edges of the same color. So if we have 1 point that breaks that requirement, we could have, for example, something like this. We actually have 5 ways to choose which vertex breaks that requirement. Let's say we did this, then we have 3 more edges that we can freely color. And since we have 3 colors, 3 edges, we would have 3 times 3 times 3 is 3 cubed ways to finish off this configuration. So we would have 5 ways to choose which vertex breaks our rules, and then 3 cubed ways to finish off each of those configurations. For 2 points, we have our first case being when we have 2 blue breaking our requirements, and then that final edge, we have 3 ways to finish it off. We could have something like 1 blue, 1 green, and then we have 3 ways to finish it off. We can also have 1 blue, 1 green this way, with 3 ways to finish that off. We could have 2 green, like this, and then 3 squared ways to finish it off, since we have 2 free edges. And then finally, we can have 1 red, 1 green. Like this, with 3 ways to finish it off, or like this, with 3 ways to finish it off. So we have 2 times 3 ways for that case with 1 red, 1 green. And then finally, with 3 points, we can do something like this. Taking advantage of the fact that the green are adjacent. So we actually only have 1 configuration where 3 points are breaking our rules. Now combining all of this calculation using pi, we'll take all of the cases where 1 point breaks our requirements minus all of the cases where 2 points break the requirements, and then add in when 3 points break the requirements to get 112 colorings. And keep in mind, those are the ones that are no good. So we want to subtract that from the total. The total is, we have 5 edges we need to color, 3 colors for each edge, so 3 to the 5th total ways. So 3 to the 5th minus 112 is 131 colorings that are good. So finally, we'll have 131 times 5 times 3 factorial. The 5 is coming from the fact that the lone edge with that single color can happen in 1 of 5 places. And then also that we chose the colors at random, but we actually have 3 factorial ways to permute those colors. So actually, our total is going to be 5 times 3 factorial times 131, which is going to be 3,930 for this case. On to the next case. Our next case looks something like this, where we have a red up here, we have a green over here, and then kind of across from that green we have another one, and then blue over here, and then kind of across from the blue we have another blue. And so again, we're going to use the principle of inclusion and exclusion. Like before, you can quickly check that, again, the same argument holds to show that the number of configurations with 1 point breaking our restrictions is going to be 5 times 3 cubed. For 2 points, because we don't have any kind of adjacent pairs of same colored edges, we actually have a nice way to count this, where we just fix one edge that we will not color just yet, and then all of the other 4 edges are going to be fixed. For example, here we're going to have to kind of break the requirements with that point, break the requirements with this point. So those 4 have been automatically fixed, and then that one that we reserved over here, we have 3 ways to finish it off. So we had 5 ways to reserve an edge, and then 3 ways to finish off that configuration. So we have 5 times 3 ways to do 2 points. And then finally, for the 3-point case, actually because we don't have any pairs of adjacent same colored edges, we will have no ways to do 3 points that break our requirements. Okay, on to the calculation parts. So we will have number of ways to do 1 point minus number of ways to do 2 points plus number of ways to do 3 points, which is going to end up being 120 colorings that are not good. And so we subtract that from our total, 3 to the 5. So 3 to the 5 minus 120, which is 123 colorings that are good. And really similarly to what we did last time, this red could have been in one of 5 places. And then again, the colorings, we fix them over here, but we actually have 3 factorial ways to permute those colorings. So we're just going to have 5 times 3 factorial times 123, which is 3,690 colorings for case number 2. On to case number 3. In this case, we have something like this, where we have a red edge right here. We have a pair of adjacent blues right here and a pair of adjacent greens right here. Again, using pi, with the same argument, we're going to get that for 1 point breaking our restrictions, we're going to have 5 times 3 cubed ways. For 2 points, we're going to have actually quite a few cases here. First one is with 2 green. So if we have 2 green violating our restrictions, then we have 2 edges that we haven't colored in yet, so we have 3 squared ways to finish that off. We can say a similar thing for the blue. Again, we have 2 free edges and 3 squared ways to finish that off. The next case is going to be 1 red, 1 green, where we take this, and then we have 3 ways to finish that off with that 1 remaining edge. We can also do 1 red, 1 blue, and then 3 ways to finish that off with the remaining edge. Or we could do 1 blue, 1 green. And we actually have kind of 3 ways to do 1 blue, 1 green. We could have 1 blue, 1 green like so. And then 3 ways to finish it off like so. And 3 ways to finish it off. Or we could have something like this. And then 3 ways to finish that off. Now we move on to the case where 3 points are breaking our restrictions. So taking advantage of the adjacent same colored edges, we could do something like this, and then use that final green one. So that's one way to do it. Another way to do it would be to have this, and then use that blue to finish it off. So we have 2 colorings where 3 points are breaking our restrictions. Now, going to the calculation sections, we would take everything where 1 point breaks the restrictions, subtract out all the colorings where 2 points break the restrictions, and then finally add in the cases where 3 points break our restrictions to get 104 colorings that are not good. subtract that out from our total of 3 to the 5th to get 3 to the 5th minus 104 is 139 colorings that are good. Very similarly to the previous two cases, we actually had 5 places to put this red edge, and then we had 3 factorial ways to permute the colors. So we want to multiply by 5 times 3 factorial to get 5 times 3 factorial times 139, which is 4,170 colorings for this case. And now we can go and combine all 3 cases to get a grand total, which will be 3,930 plus 3,690 plus 4,170 to get 11,790 colorings. And then we go back up to the original problem to check that that was indeed one of our answer choices. And yes, we do see it right there sitting at answer choice C. And so we circle it, and we're done.